Good morning, everyone. Bright and early today. I'm waiting for the good morning back.
Good morning.
Good
Good
morning.
morning. Good to see you all again. So, today we're going to abandon the ANOVAs because for now we're done with them. We've covered a lot of them. I think, at least with the mixed design ANOVA, you have enough tools to be able to come up with some pretty experimental designs and be able to have statistical analysis that fit designs where you have repeated measures, where you have a control group, where you combine those two, where you can even add interaction terms to it, both for the repeated factor or for the within factor. So as far as the ANOVAs are concerned, I think we have enough. As you have seen, I think we discussed in the last lecture that there are even more possibilities than we've shown you in this course. One was, for example, that even within the mixed design ANOVA, you could add a covariate to control for some confounding variable. And we've seen that we've discussed shortly that it's even possible to not have just one outcome variable, but have a couple where you could even do a multivariate analysis of variance. So there are more options out there, but we will leave those for follow-up courses that you will follow doing your studies. So for today we have the chi-square test scheduled, and the chi-square test is an interesting test because it's based on the chi-square distribution. So we'll be looking a little bit into that, but it's interesting in the sense that it's a test of its own, in the sense that you can perform a chi-square analysis, a test to essentially determine the I would say correlation, but then at categorical values. So what we've seen with normal correlation is that you have a relation between two continuous variables, where you could have any value on the x-axis and any value on the y-axis, and you have the dots that represent the relation between the score on one variable and the score on the other. But the entire chi-square test is based on categories. So instead of having having a continuous variable, you have just, are you part of category A, B, or C on this variable, and on a different variable you could also ask the same question, are you part of group A or B? So on its own, it's able to test some hypothesis on the relation between two categorical variables. But what you also see is that it's used a lot to as a sort of measure of standardization. So one of the assumptions in a lot of the research that we do is that we have a random sample from our population, and we use that the fact that it is a random sample to essentially justify our statistics. But in some cases you could imagine that there are some variables where you can assume that if there's a disbalance on this variable for your research design, for the categories you created for your research, the thing that you're interested in to see if there's a difference, then this can be problematic for your outcome. So, for example, if you have a control group and an experimental group, and it would happen to be the case that in the experimental group there are many more men than there are women in comparison to the control group, then that fact would skew your results. Because if you're interested in the experimental effect in general, not just specifically the difference for males and females, then it would not be good if you have the experimental group only containing mostly men. So even if you do a random sample, it could be the case that you have more men in the experimental group than women. So you could use the chi-square test to see if there's essentially a correlation between gender and the control group and the control groups that the groups that you've created for your research, where in that case you actually want there to be no correlation. So if you do a chi-square test, then the goal is to find no significant difference in the two, because you want the proportion of males to females to be equal, or at least somewhat equal in both groups. So you see that the chi-square test is used for these kinds of purposes also, and but can also be used just to answer research questions that you have on your own. So that is about the chi-square test. We're going to go into the a little bit of the concepts. We're going to do the some calculations on this, and we're gonna look at some research where a chi-square test is used primarily to answer some hypothesis. So we'll be looking into that. So what I'm showing you here is well, actually the way the chi-square is calculated, and it's essentially based on matrices. And this sounds very complicated, but it essentially isn't. It's just the observed frequencies in your data versus what you would expect if there were no, if you would assume that nothing would be going on, essentially. So what we're seeing here in general terms, it's stating essentially the same as we've been seeing with all our models. We presume that the outcome is equal to the model plus the error, and here we're essentially doing subtracting the model, the expected values, from the observed values, which is the outcome. So it's essentially, well, an error term in that sense that you could use. So we're seeing the same kind of reasoning. So we have the observed values and the thing that we expect, and we have to look a little bit closer on what, for example, is stated here. So we have the observed values, and you see that it's subsetted with an I and a j, and that I and j refers to the matrix that you're looking at. So, for example, this is the matrix of observed values, where I stated that we have O's from observed, and we have 1, 1. So this ij refers in this first cell to the first row and the first column. So it's 1, 1. And this one refers to the second row, but we're still in the first column. And this one refers to the first row, but the second column, etc. So what are these cells? Well, they're actually, in terms of the observed values, the frequency that you have within a combination. So if you're talking about you have males and females and you have an experimental control group and an experimental group, then that's a 2x2 design. So this matrix would not be as large, but it would really stick to 2x2, having either the category males and females and control group and experimental group. And what we're putting in these cells is just the frequency of males in the control group, and then here you would put the frequency of the females in the control group, and the number of males in the experimental group, and of course the number of the females in the experimental group. So it looks a bit daunting if you look at this, but it's just how many people are in which categories. So you just combine your two categorical variables and fill in the amount of people that you have in the cells. Does that make sense?
Yes.
Good. Okay, so well, the chi-square test is essentially a bit of the same kind of test that you do with an F distribution. It's starts at 0 and goes up to infinity. So the shape of the distribution looks a little bit like an F distribution. So that also means that for the same reason as for the F distribution, that you don't test two-sided because you can only go one way. But it does have a few degrees of freedom. So determining on the degrees of freedom, which are defined by the number of rows that you can see here, and the number of columns -1 multiplied for the rows and the columns. Those are your degrees of freedom. And every time we have some probability distribution that contains degrees of freedom, what does that mean? What does it mean if a probability distribution has degrees of freedom? In terms of the shape of the distribution. Anyone?
Well, the shape changes depending on the degrees of freedom.
Yes, very good. So, where you, for example, with the normal distribution, there aren't any degrees of freedom. So the shape of the normal distribution is always the same. And we've seen with the t-test that we have a degree of freedom which determines the thickness of the tails. We've seen that the F distribution has 2 degrees of freedoms, one for the error and one for the model, which determines, well, not just the height and but also how much it's skewed to the left or to the right. And the chi-square test also contains the degrees of freedom. So that's a very good observation, that if you have degrees of freedom within your distribution, that means that we could have different shapes of our chi-square distribution. So depending on the number of categories that we have in our two categorical variables that we want to compare, the shape of that distribution is different. So if we look at those shapes, well, we see it's wildly different for the chi-square test. And what I've shown here is the number of the degrees of freedoms expressed as k, where the first one we only have 1, which is a bit weird, right? Because you should have 2 by 2. So, but it is possible. You could just stick a 2 degrees of freedom in your chi-square distribution. The reason is because it can also be used for different kinds of analysis. It's not just stuck to the 2 by 2 matrix. matrices. As you actually have seen, I think with the non-parametric test that we did, we also used the chi-square distribution to determine if there were significant differences within the non-parametric tests. We used the same chi-square distribution. So up until 10 degrees of freedom, we see that the shape differs. So what are we looking at here in terms of null hypothesis significant testing? So what do these distributions represent again?
Is it the sampling distribution if the null hypothesis is true?
Yeah. So indeed, it's about the null hypothesis being true, and you're also right to call it the sampling distribution, not the sample distribution, but the sampling distribution, meaning that if we took a sample and we'd calculate, well, our chi-square value, and we do that over and over and again under the assumption that the null is true, we would get shapes like these. The small difference is that it's the continuous chi distribution of that sampling distribution, because if we actually had a sampling distribution, it would be, well, just like we've seen with the sampling distribution that we created for the f value. It would be bars or a histogram containing those binned values, and now we have the continuous slope of the chi-square distribution. So, but the most important part, where you're absolutely right, this is assuming that there is no relation between the two categorical variables. So, assuming the null to be true, this is the shape of the probability distribution. So, so that also means that, for example, look at this this green one. Where we have 3 degrees of freedom. So the shape of such a distribution is a lot different. So it really means that you even high values of chi-square happen very frequently within these specific degrees of freedom values. Whereas if you would have a very low degrees of freedom for example, this red value, even a value of let's say 3 is something that does not happen very often. And so what we're seeing here is essentially the null distribution. So the same holds in the interpretation of this null distribution and the results from our data as was for the f values that we did and the t distribution. You assume the null to be true, you find your data, you put your data, your data that you find will have some value on the chi-square test, and you see what is the probability of such a value or more extreme under this assumption, and you compare that, of course, to your chosen type 1 error rate, your alpha. Okay, still clear?
Could I ask a question?
Of course, always.
How do you make a continuous graph from two categorical variables?
Yeah, so it's not the continuous graph of the variables, right? It's the continuous graph of all possible chi-square values under the assumption that the null is true. Yeah.
Okay,
so it's
thank you.
Yeah. So it's the same as you would have with a t-test, where you essentially also have two categories, namely the two categorical variables of your independent variable, but you make a t-value and that t-value is a continuous value.
Thank you.
Okay, you're
Could
welcome.
I just ask you, you just said
Sure.
1 degrees of freedom is uncommon, but we apply this chi-squared test quite often to a 2 by 2 contingency table. Wouldn't that give you 1 degrees of freedom?
Is that right? Yeah, you're probably right. So it's 2 minus 1 adds 1. Yeah, you're right. Yeah. Yeah, good point. Sharp. Very good. So because it's a 2 by 2, you have 2 minus 1 is 1, and 2 minus 1 is 1, and 1 times 1 is still 1. So yeah, you're right. Okay, so I want to do an example, and we're going to look at some research by Simone, and let's see, I'll try to get it in view. It's this one. It's some research performed by Armando Simon, and it's research about whistling. I don't know if Roland mentioned this in his lecture. He did at one point, but did he?
No.
No? Very good. Then I've got the scoop. So Armando did some research on whistling and gender difference, and this was published in the renowned Journal of Gender Studies, published by this amazing publisher called I don't know how it's spelled, Routledge. Well, so we're not gonna. I'm not gonna. Well, I'm priming you, of course, to judge, but. First, we're not going to read it, and we're only going to look at it. So we've got the introduction, the method section, the results, and the discussions, and we're done. So, yeah, this is a published article, but, well, we'll go into this, because... So these things happen somehow in research, that it's possible to publish such articles when essentially a short article is not a bad thing, because if it's very good, then well, okay, it's very good, so that shouldn't matter. But we're going to look into this. So I'm gonna ask you some questions based on the article that Simone published, and we're gonna read this part for a second. So, casual observation by the present author, that's going through the empirical cycle, so that's good, led to the hypothesis that whistling might be yet another instance of gender differences. Well, we've got some famous people being referred to here, and then comes the part where we state our hypothesis. And so from this casual observation, it was hypothesized that more females would report an inability to whistle, and that males would report whistling more frequently than females. It was also hypothesized that frequency of whistling would diminish over time. You got this? So my question to you is, and you could also write this down for yourself, but I want to have a bit of a discussion about this. So what would your analysis be that you would perform based on these hypotheses? So let's split them up. So we're gonna do the first. So from the casual observation, it was hypothesized that more females would report an inability to whistle, and that males would report more frequent. Okay, this one. Go ahead. So what do you think that should be the analysis that would be associated with this?
Wouldn't you say for the first part that it would be a chi-squared, and then for the frequency of whistling it would be a t-test?
Okay. What is your argumentation for this?
Well, for the first quark, so the females would report an inability to whistle. You could put inability in a contingency table with zeros and ones, so you are or aren't able to do it.
Yes.
And gender, you can also report with zeros and ones.
Very
and
good.
For frequency, well, you just have two groups, and you want to have the means, so how
Yeah.
frequent you whistle,
Yeah.
and compare
Exactly.
those.
Well, sounds very plausible. Very good. So we'll keep that in mind because I think this is a good strategy. And if I read this this line, I would also opt for doing a chi-square test because you're saying, well, females would report more inability to whistle. I would even state that in terms of stating your hypothesis, it could be more explicit, in the sense that he says that reports more females would report, and implicitly saying, well, it's not clear what he's implicitly saying, because I would assume, as you assume, that if you say someone reports something more, then I want to know compared to what. So if you're saying I'm reporting more than males, I would assume here, and he's flowing into essentially the next hypothesis. So you're a bit tricked, because he says, well, more females. I have to go this way. Yeah, more females would report inability to whistle, and that males. So now he's flowing into the next hypothesis, as you clearly stated, about an hypothesis about males. So I think I would be more clear on what you're actually trying to compare in your hypothesis, because it's a bit vague, and we're going to see what the results of this would be. So and the other part was that males would report whistling more frequently than females. And you're saying, well, you're treating then the frequency of whistling as a continuous variable, which is, I think it's plausible that it would be continuous. And in that case, you would opt for an independent samples t-test, where you would just see, well, what is the mean frequency for the males, and what is the mean frequency for the females. And the final part, it was hypothesized that the frequency of whistling would diminish with age. So what would we do here? Anyone else?
Maybe another t-test, but then with the variable of age.
Yeah, and so what would be then the independent variable within the t-test, and what would be the dependent variable with the t-test? And which variables would you have?
So then the dependent would be the frequency, and then independent would be age.
Okay.
Because in this particular hypothesis, they don't say anything about gender, so I don't think that should be part of the analysis in this case.
Yeah, I would absolutely agree that the hypothesis is not stating anything about gender. So it's only about the relation between age and frequency. Does anyone agree, or is there anyone that disagrees with performing a t-test on this one?
I would think it's a Pearson correlation.
Why?
Because I saw it on the table.
Because it's set on the table. Okay.
Yeah.
No, but you have to give me some reasoning. And can you? And maybe anyone else? Why you would think that would?
I
up.
think it's because age isn't categorical
Exactly.
like gender is.
Exactly. Age is well somewhat I think a continuous
Famous.
variable. So because you're doing the continuous variable comparing to another continuous variable, then you would do a correlation, and then of course you could have the discussion about are the assumptions met. So you could do either a Pearson or a Spearman correlation based on if you want to do the analysis parametric or non-parametric. So those are the two options that you would have. But the correlation here is the only good option, and because the t-test assumes the categories. So that's very good. Okay, so keep that in mind. We want to do a chi-square test for males and females. We want to do what was the other part again? The t-test for the frequency, and we want to perform a correlation for the frequency for and age. Okay. Now, before we go into the results, we're gonna first read the entire chapter on the method that is used. A very brief survey was administered asking subjects their sex, age, and whether they could whistle, and if so, with what frequency. 20 college students utilizing the college library, blah, 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 took part. So we have 20 people here. And then he has another 45 people from this newspaper distribution warehouse where we administer. So that's not a very large amount of not a very large sample, but it's decent. And I think he even goes so far at one point to note that this sampling is better than using the standard psychology student because it's more representative of the general population. I think. Here's where he states that the author agrees that the criticism leveled at studies that solely utilize college students as subject is valid. Citing some research again, a bit trivial. So he really pats himself on the back that he's able to use some workers from this factory, from this warehouse to do the research. Well, okay. Now here we go with the results. Of those subjects that claimed to be unable to whistle and did not proceed to answer the remaining question, 4 were males and 5 were females. Okay. The correlation between age and frequency of whistling was significant for females, but surprisingly not for males. The results indicated that men whistle more often than women. The chi-square test for frequency of whistling and gender was 7.03. Okay. So what is he doing here? Tell me.
He's messing it up.
Yeah, he's certainly messing it up. Totally agree. So, but what is he actually doing? So he's doing a correlation. Well, we thought of doing a correlation too, yeah. Correlation between age and frequency. Well, we thought about that too. But his hypothesis was not about this correlation having any impact on the gender. So he's splitting the correlation part up into a part for males and a part for females. So he's saying, that could be, that there is a but that's not answering the hypothesis that he had, because he had a general hypothesis about age, the relation between age and frequency of whistling. And okay, he concludes that that does not hold for males. So okay, but it's not related to your hypothesis. And then he goes on to the results indicated that men whistle more often than women. So this is trying to answer the hypothesis that we had this for ourselves, that we determined also, right? The frequency of whistling and the difference between males and females on this. We thought that we should. What did we think again?
We were going to use the t-test?
The independent t-test, yes, right? Because we're assuming the frequency of whistling to be a continuous variable. And what did he do? He applied a chi-square test to the frequency of whistling and gender. And that was significant. Wow. Could you argue that this is a good... this specific one is a good analysis? Is it a good analysis? Could you find a way to argue that performing a chi-square test for this specific question, namely differences in frequencies for males and females, to do this with a chi-square test?
Maybe if you would categorize frequency by doing like sometimes, often, or always.
Yeah, exactly. So you could find a way where this would fit. So if you would indeed categorize your the frequency variable, then it would be plausible to perform a chi-square test, because then you would have a categorical variable that you want to compare to another categorical variable. So if we look at the method section, can we find out if he actually asked for the frequency or the categories? A very brief survey was performed asking subjects to sex, gender, with the frequency. Yeah, they could whistle, and if so, with what frequency? So I do assume that he asked for the frequency, because otherwise he would have stated here that he would have done, he would have created categories, right?
Yes.
Yeah, I think so too. So he still could have transformed the continuous frequencies into categories, but he doesn't state that that he's actually doing that. So in that sense, that's not good reporting. And can you think of what would be the problem with categorizing your continuous variable? So if he chose to categorize the continuous frequency variable into categories, what is the problem with that?
Well,
Go ahead.
if the categories are too wide, and for instance, like people of the same category still show a significant difference between their frequencies, you would miss the difference.
Yes, could be. And related to that point,
There's no objective way to split.
exactly. So
Okay.
and that's a very important point. There's no object. Well, you could argue for a few, but it allows for subjectivity in the categorization. So I could create some categories and look. Well, if is there a significant difference? No. Oh, I'm gonna make my categories a bit wider. Is there a significant difference? No, still not. Oh, I'm gonna make them wider, because you know from statistics that the more subjects you have in your sample, even in a category, that the narrower the distribution gets. So having more subject will increase the chance of you finding significant results. So it introduces a very subjective measure on this part. So you could imagine that you would split your data into equal parts, where you use the bin function that we've done, I think, in the beginning of this course, to split it at equal parts. That would be a little bit objective, but well, you have the continuous variable, so why not just perform the t-test here instead of doing this? Another thing that could have happened is that people reported the frequencies, and there were a very it could have happened that people reported the same frequencies. So let's look at this question again. Whether and with what frequency? No, it's not stating anything about that. Age. It could have been that, for example, 10 people said I only whistle once, and that the other 10 said I whistle twice. I think it's a week, but I'm not sure. And so it could have been that the frequencies the data that he gathered was actually not continuously distributed. So it could have happened that this was the case, and that he just thought, well, I only have 3 or 4 categories of frequency levels, so I'm gonna use a chi-square test instead. That could have also happened, but again, he's not stating it. So I'm using this example to also emphasize the importance of good reporting, because as a reader, I'm seeing here that there are analysis done that I can justify if I read this article. So you have to justify as a researcher the choices you make, and that's something that Simone doesn't do here. And actually, what is missing from the results? Oh, sorry. What is missing?
The degrees of freedom?
Also, yes, we're missing the degrees of freedom in your chi-square value. But there's a complete analysis missing here.
The analysis of ability to whistle and gender?
Exactly. So the main point that he has on this article, the title of the article, yet another gender difference, he doesn't even give an answer to the question, is there a difference in whistling between men and women? So, well, okay. It's quite insane, isn't it? So how would you judge this article in terms of research? You think it's good? You think it's bad?
Short and to the point.
Sorry?
It's short and to the point.
It's short and to the point. Yes, it sure is.
But to the wrong point.
Yeah, that's true. It's also to the wrong point. More comments?
Why was it published?
Oh, that's a very good question. I'd really like to talk to the publisher on how this review process worked. So that's also an important point. So I think we agree that the quality is not really good. On the other hand, I don't really mind that this stuff gets published, because I can read it and I can determine on my own if it's what the quality of it is. So I can I can see that, well, we have some issues here. We have a lot of issues here. Okay, I'm going to ignore this research and maybe write a comment on it, or maybe even try to do it myself. Try to replicate this study and even do it better than Simon did himself. So why don't we do this today and try to replicate this study and analyze it as it's supposed to be. So what I'm going to do is I'm going to drop this URL in the chat, and I'm going to ask you to fill in this this form. And I'm going to ask you, well, essentially the same questions as Simone asked you. I would like to, oh, it's Dutch, I see. Fluiten is whistling. So you have to choose if you're able to whistle yes or no. You have to give the frequency. I also ask you how assertive you are. Gender. And your age in years.
Is it how often you whistle per month in days, or like time, like literally?
A month. Yeah, sorry. So how many times per month you whistle?
Yeah, but if you whistle twice on one day, is that twice or is that one day?
Good point. Yeah. So, yeah, how many times a month? Yeah, you go ahead. And this is an important point, right? Again, so if you're looking at this questionnaire and you have these questions, that means that it's not concise enough. If you want to be precise, you have to be precise in your wording. So the frequency per month, well, that could be more specific. I think also if you look at this one, age is also a bit problematic, right? Because what do you want in age? Do you want this in years? Or maybe you put down your birth date, or how precise do you want to be? So seeing such a questionnaire and well, I'm doing this well, as pure fun. I'm never going to publish something out of this, but you already see that if you have ambiguity on these questions, that is going to result, that's going to skew your results and have an impact. So you have to be very precise, and well, it's good to see that in action. So is this working? Are you able to fill in the results?
Yes.
Very good.
Yes.
Cool. So what I'm going to try to do now is rerun my entire presentation. And that should update all the analysis that I perform in the presentation with the results that you've added. I'm doing this behind the scenes. Yeah. New data, added, commit, and push. Yep. So what I've done is rerun the slides. It should update in a few minutes, and I would suggest that we take that time for the updating of my slides to get a cup of coffee. So we're gonna do that. My doorbell is ringing, so I'm gonna also open the door, and I'll see you at 10 o'clock. We'll continue. Okay?
Okay.
See you then. Okay, so we're continuing. There were some construction workers at the door, so they have to be in the building, so maybe there's gonna be some drilling. I hope not. Okay, so we've gathered your information. Let's see what happened here. I've got the data here. As you can see, I started this in 2017 already, with the same questionnaire, gathering info. And let's see if we go to the last one. This is, yes, this is today. So your data is now in here, and we can use the data combined from 2017 up until today to do our analysis. So we'll do this. So we're going to calculate first the chi-squared test, and I've bothered you a bit with the matrix notation, but well, it's not that hard. It's just putting things in a table and stating that it's a matrix in essence. So if I want to have, well, the main hypothesis here is there a relation between gender and being able to whistle or not. It could be yes or no to whistle, and you could be either a man or a woman. So the observed frequencies that we find are 29, 58, 32, and 3. So that means there are only 3 men that can't whistle, and there are 29 men that can, and the women report that the 32 of them cannot whistle. So maybe Simone is on to something, right? So getting to the observed values is well, easy. It's just plugging in the frequencies. So the next thing is that we want to essentially determine what the model is, what our expected values are based on the frequencies that we find. And this is done by essentially looking at the proportions that you have by the combined columns and rows to the total, because if the relative margin, the relative margins are equal to what's happening inside the cells, then there's nothing going on. But if inside the cells the frequency is relatively different than what you would have in the margin, and with margin I mean what we're seeing at the outskirts, the totals of the rows. So we have people that can whistle, 29 males to 58 females, and the total, those are the margins. It's the sum. So to get for each ij the expected model value, we have to look at the row total for I and the column total for j. So if I want to know what the expected value is for males that are able to whistle, I have to look at the row total. Well, this is the row, so I have to look at this one. I have to multiply it by the column total for the cell that I'm interested in, still the males. So that's 32, and I have to divide that by the total amount of observations that I have. And with those two, I get the expected value, the expected frequency for the males in that can whistle. And I have to repeat that step for all the males that can't whistle, and for all the females that can and can't whistle. So this needs to be done 4 times essentially. So if I apply this, so what am I doing here? I want to actually do this. So what I'm saying is that, well, I have to do it for the first one. So it's the row total and the column total. So this is the column total and this is the row total. I multiply these, divided by the total amount of observations that I have. I do it for the second column and the the row total for the first, and again for each and every cell that I have, I calculate the expected value, and that results, because what we're seeing, we aren't seeing a sum function here. What it results is a matrix again, but then with the expected frequencies for each cell. So doing that and putting it in a matrix again, I see that we have 22, 9, 64, and 25. So these are the results that I get with R. I also put them in a bit of a formal notation, putting them in the model IJ matrix. And what I want to know now is, well, how much does my data deviate from what I would expect based on the margins? So I have to simply subtract the model from the observed values. And so essentially it means having the matrix for the model with 4 values, and you have the matrix for the actual observed score. So to get to the new matrix, you just have to subtract all 4 values. So we have to subtract 22.8 from 29, and we have to subtract 9.1 from 3, etc., etc. And that's what I've done here. But because I've put everything in a matrix, I can also just subtract the matrices. So that's what I'm doing here, and that results in my the things that we're left with. So for the final step, what we're seeing is that we have to add this all together, essentially getting rid of the zeros if we sum it all up, just like we did with the sums of squares, with the method of these squares with the ANOVAs. So we're squaring the distance between what we observed and what the model is. So we just means square all these distances. And we have to divide this by the total model. So everything we were expecting again. So this means that if you divide this for your entire model, it means that every cell of your matrix, you have to divide it by the value of that cell. And then it's a question of adding those values. So it's essentially saying sort of standardize your residual in essence, and that's what we're doing here, and that gives us a value of 7.9. So the chi-square value that we eventually get is the sum of the difference between my observed scores and my expected scores squared, divided by what we would expect, again, the model, which results in a value of 7.9. We've already stated that we have the degrees of freedom, And as was remarked earlier, you certainly can have a degrees of freedom of 1 because we have 2 rows minus 1 is 1 multiplied by 2 columns minus 1 is also 1 and 1 times 1 is still 1. So I've got 1 degree of freedom. The 1 degree of freedom was the red one, right? Remember? I'm going up all the way. The 1 degree of freedom is the red one. So do you think that this is a significant result?
Yes.
Absolutely,
Yes.
yeah. Yeah, very good. So you're seeing within the null distribution that the probability of getting even a 6 or higher is very low. So the area under the red curve, well, it's almost flat. So if I'm getting a result from a result of 7 point something, 7.9, well, this is higher. So even though Simone didn't do a really good job with his setup of his research, he's still onto something. There is a difference between gender and being able to whistle, as these results show. We're going to perform again the visualize function. So it's again the visualize function, but this time with a chi-square distribution. We've done this before with the non-parametric tests. We have to provide the chi-square value and we have to provide the degrees of freedom. We have to set the section to upper because it's not a symmetrical distribution. And that results in our distribution being shown here, but our chi-square value is so extreme again that it falls off the chart here. So what it's stating here is that a chi-square value of higher or equal to 7.9, the probability of that under the null is 0.004. So there is a significant difference here between males and females, and being able to whistle or not. I have to make one slight remark on the sidedness. Let's state that the sidedness of the chi-square distribution, because as you can clearly see from this distribution and also from the previous distributions, it's clearly one-sided. But the chi-square distribution comes from a family of distributions where it's actually a symmetric distribution, but that symmetry is squared, and that results in the chi-squared distribution. So there is a relative of the chi-square distribution, which is actually a symmetrical distribution, and that distribution is squared, and that results in our chi-square distribution. But I'm telling you this not for fun, of course, but because if you run an analysis in SPSS, a chi-squared analysis, then it reports your p-value as being two-sided, and that is very confusing because it's obviously not a two-sided test, and it could also lead you into the temptation of dividing your p-value with 2, and that's not supposed to be the case. So be warned, when you perform the chi-square analysis in SPSS, the column in SPSS states two-sided, but you have to ignore that. You just have to report the p-value as is stated.
Sorry, can I just clarify that? Because I didn't quite get it.
Yeah, so the main upshot is that if SPSS reports the p-value for a chi-square test, and it reports it as two-sided, you should not I repeat, you should not divide that p-value with 2. You should just take the p-value as it is in the chi-square results.
And in R, it would show it one-sided.
Even if you do a chi-square test in R and use the chi-square function in R, it also states two-sided. So
we should just we should always report the two-sided value.
Yeah, exactly.
Okay.
Yeah. Okay. So now there are some situations where the chi-square results are a bit skewed, especially when you have a small sample size in one of the cells. And in our case, we did have a small sample size in one of the cells, I think. We had 3 here in the cell for the males that could not whistle. So there are some corrections available also within SPSS, and Field covers these. And one of them is the Fisher's exact test, which you can do if one of the cells has a smaller observations than 2. So instead of calculating the regular chi-square value, you would calculate the exact chi-square value, the Fisher's exact chi-square value. And essentially it's the same here, what we're doing, but he provides a slight correction on the difference between the observed values and the model, essentially on the absolute difference on these two, and that slightly corrects the chi-square value and making it a little bit less prone to having wrong estimations of your p-value, because you can imagine that if you're if the assumption of the null holds and you determine what the shape of your F distribution of your chi-square distribution looks like under that assumption, you could also try to hold that assumption, but with a small sample size in one of the cells, and you could see what does the chi-square distribution look like in that case, and what was found by Fisher is that if you have such cases, the distribution of the chi-square under the null is a little bit different. So if you would not correct, that would mean that the p-value would not actually indicate the correct probability of choosing to reject the null hypothesis, because the null distribution is actually not the null distribution in that case. So you don't have to be able to go into the details. It's just to know that if you have such a case, then you could perform a slight correction on your chi-square analysis. And if I perform that here by using the absolute difference and subtracting 0.5, dividing by the model again, then I get a chi-square value of 6.6, which I also think will be significant. And even if we test this again with the visualize function, we see that we still find the probability of getting a chi-square value of 6.6 or equal to 6.6 or higher is still lower than 0.05. So we're still finding that there's a difference between males and females in their ability to whistle. Maybe we should contact Simone.
I have a question.
Tell him that he's right. Go ahead.
Is it when the cell size is smaller than 5 or smaller than 2? Because in the slide it said 5, but I believe you said 2. So
in the slide it says 5. But
okay, so 5.
Yeah. And I'll look into it, but I think Field also mentions 5. Yeah. Am I stating it wrong somewhere? What do you mean? What are the?
No, I think you said
that's why.
2.
Oh, I
so
said
I
2.
got a
Oh,
little bit
sorry.
confused.
Okay, I misspoken there. Sorry for that. So that's the Fisher's correction. Yeah. Am I skipping something now?
I think we're on
this
to the
is,
likelihood
sorry,
ratio.
no, sorry. I've applied the Fisher's exact tests, and we're going to the likelihood ratio now. Yeah, I lost my track. There's also, and this is just for your knowledge, there's also an alternative to the Pearson's chi-square test, which is the likelihood ratio, and in essence, it states the same thing on your data, where you create a ratio of the observed values and your model. So instead of subtracting the difference between what you actually found and what you would expect, you're using the ratio between them and multiplying that by the log of that ratio. So it's a different way to view the same contingency table and get to an alternative distribution. It's still chi-square distributed, but this likelihood ratio could also be used for this. And even if we apply this, we get still a significant result here. So I just put these in there because Field covers these. SPSS output provides these, and at least you know the difference between the two. And there's no preference in using this one to Pearson's chi-square distribution. What is important is the interpretation again, because just like when we performed the analysis of variance, such an analysis of variance only states that that there is a difference, and especially when you have more than 3 groups in such a one-way independent ANOVA, for example, it doesn't specify where the difference actually is, and that also holds for our chi-square test. So a 2x2 contingency table would indicate, if you find a significant difference, would indicate that there's a relation between the two, but it doesn't specify what that relation is. So we could, of course, look at the observed scores, what we did, of course, in the beginning, and we noticed that we only have 3 observations, that are only 3 men that indicate that they can't whistle. So you could eyeball it in that way, and of course you could also look at the absolute difference of what you expect from what you observe. But if you look at if you do that, then you always have to relate it to the scale that you're measuring with, and in this case the scale you're measuring with is the amount of people in each cell, and that could vary from experiment to experiment. So if you could standardize this, then the way you would interpret this would be at least the same for each and every experiment that you do. So one way to look at what the differences are and where you can find those differences is indeed to standardize your residuals. So what we're doing here is, looking at the difference between the observed scores and the model. So that is essentially the residual again. as I stated earlier. And if we divide this by the model again, the square root of the model, then we actually standardize. It's basically the same principle as you're applying with default standardization, right? Where you're saying you look at the difference between the actual scores and the means and subtract and divide that by the standard deviation. Well, it's the same principle here. But because we are applying this to a matrix, you also get a matrix as a result. So by doing so, we see that after standardizing, these are the results. So what do the values mean again, now that we've standardized? What do the values mean that we're looking at here, now that we've standardized, in terms of the size of these values? Anyone?
You can more easily compare.
Yes, you can more easily compare, indeed. But what do the values mean? What is the essentially the scale of these values that you now have?
Are they z-scores?
They are exactly z-scores. They are standardized. So
standard deviations?
Sorry?
I said maybe standard deviations?
Exactly. So each unit of 1 is 1 standard deviation from the mean. So having scores of 0 here means no difference in the observed value and the model. But having a value of 1 tells you, oh, this one is a bit more than 1 standard deviation from what we would expect. And this one is even slightly more than 2 standard deviations than we would expect in the negative direction even. So because you've standardized this, it's easier to interpret, yes, of course, but it's easier to interpret because you now know what the meaning of the value is. 1 means 1 standard deviation off, instead of it being a frequency of 6 or 8 or 4, then you think like, well, I don't know, is 4 large or not? And now you know if it's large or not because it's expressed in terms of standard deviations. Does that make sense?
Yes.
Yes.
Okay. So now, based on our data, we can clearly see that there are a lot less men that aren't able to whistle, and there are relatively more women that aren't able to whistle. So it's still in line with yet another gender difference from Simone. So this is one way to look at it, just looking at the standardized residuals. The other way is to look at effect sizes, and these effect sizes within the chi-squared distribution actually looks at, let's say, ratios that you have within each cell. Between the cells. So it's actually meaning that you can have multiple effect sizes. And the meaning of the effect sizes is a little bit different depending on what route you choose. And Andy Field is not very explicit in what route you should take. So I'm gonna show you a different way here, and I'm gonna compare it to the way Andy Field does it. And what I've done here is, when using a contingency table like this, we have being able to whistle yes or no and gender on the X scale, for that matter, I've put letters that associate to the cells. So we have A, B, C, D. A, B, C, D. And if I use that, then I can calculate the effect size expressed as an odds ratio by multiplying A times B and dividing by 58 times 3, and that will give me an odds ratio of 5.3. As an indication of effect size.
You mentioned that you multiply. So in the formula, it's A times D, not A times. So you said something.
Oh, sorry. Yeah. It's A, B, C, D. Sorry. Am I doing it correctly? No. Oh, sorry. No. It's A times D. So, it's a good point that you're making. So I'm stating A, B, C, and D as the place where they are in the contingency table. But then to get to the odds ratio, you have to multiply A times D and B times C. So A is this position, D is that position, and B is this position, and C is that position. So you're multiplying the diagonals in essence. Does that make it more clear?
Yeah, but I have a question, because in the weekly assignment you have to calculate the odds ratio as well, but there to get to the result you have to calculate B times A and D times C.
Yeah, so I will show you the way Field also does it, and because what we're doing now is we're getting the effect size, we're getting the odds ratio, but we're getting a very specific odds ratio, and we could flip it around. So for example, if we would have put gender on the y-axis and whistling on the x-axis, you could still calculate an odds ratio, but then the meaning of the odds ratio would be different. So I'm gonna look at the way Field does it, and I wanted to show you both because it's a little bit arbitrary which route you choose. So if you know that if you go this route, it always gets you to an odds ratio for the variable on the y-axis, then you know how to apply it instead of, well, he's formulating it more in words, which makes it sometimes a bit hard which one you have to multiply with what. So what Field is actually doing is the men and women ratio of people that can whistle and the ratio of those that can't whistle. So he's splitting essentially the whistlers and the non-whistlers. So in his first odd, the ratio that he's creating, it's for the people that can whistle. So it's a ratio of 29 to 58. So and then he's looking at the people that can't whistle, which is a ratio of 3 to 32. So it's the ratio of people of males to females that are able to whistle, so that's 0.5, and it's the ratio of males to females that can't whistle, and that's 0.09. But then he isn't done yet, because he makes the next step here, where he's actually looking at the odds of those odds. So my odds ratio here is a ratio of the relation between people that can whistle, the ratio of men to women, versus the ratio of men to women that can't whistle. So the odds ratio that he's calculating is the ratio whistlers to non-whistlers, and that is what's given in these odds. So the meaning here is determined by what you choose here, because you could very well have also decided to say, well, I'm not doing the whistlers to non-whistlers. I could also pit the males to females and go for the ratio of whistlers to non-whistlers and get an odds ratio instead of whistlers and whistle and can't whistle. You could get calculated in a different way where you have the ratio of males to females. Are you getting me?
Yes.
Yes.
Yeah.
Okay.
Yes.
Because it's very it's very confusing. So you can look at it from the row side of things and calculate an odds ratios for the rows, or you could even calculate an odds ratios for the columns. And what I'm doing here is providing you a bit of a structured framework which you can just apply to get to the odds ratio of whatever is on the y-axis. So instead of finding out which one you have to compare, you could just say, well, I'm doing the odds ratio of the y-axis, whistlers to non-whistlers. And if I want to do this, I do it this way: A times D divided by B times C, and then I've got my odds ratio, instead of going through the multiple steps. It's both good, it both works. This one is a bit it's a bit unclear to see what you're actually calculating, because you're multiplying by the diagonals. This one, it gives you stepwise a little bit more clearance on what you're actually doing, but it's a lot of steps, and you can make can make a mistake on that. But the end result essentially is the same. Does that make sense?
Yes.
Yes.
Okay, very good.
Question about this.
Go ahead.
In a preparatory assignment, I was trying to do this, but I did it in like Fuchs way.
Mm-hmm.
But how do you know which odds you are calculating? Because if you turn them around, so you do can whistle and then the odds of female male,
Mm-hmm.
then you get a whole different number at the end. But how do you know which one goes first?
Yeah, that's a very good question, because it's not just it's not just in terms of how you formulate the calculations. It's also your personal choice on which variable you put on what axis. So if I would have created this this contingency table flipped around with the gender on the y-axis, and I would have applied this rule, I would get the odds ratios for males and females. So applying this rule at least ensures you that you get the odds ratio on whatever is on the y-axis. And this route, well, you have to figure out. So, for example, if I would ask you to give me the odds ratios for gender, well, then you have to consider which odds ratios then you would actually need. So you have to now figure out for if I want to make it for gender, and I see that and you're given data that looks like this, which has gender on the y-axis, well, then you have to figure it out for yourself, right? So it would be the odds of being able to whistle yes or no for males. That would be a ratio of 29 to 3, and the odds for females of being able to whistle or not would be 58 to 32. So
it depends on the question,
it depends
which
on
you're dividing by what.
exactly.
Basically.
Very good. Yeah.
But again, how is this related to the effect size? Because can you get multiple effect sizes?
Yes, so you have effect size for your specific odds that you want to say something about. So that's a very good observation, that with our effect size of a t-value or our effect size of an f-value, we only had one measure which just stated the amount of effect. And now with these odds ratios, yeah, well, we have an indication of the size of effect, but it is very specific to what kind of effect, which is not really that strange of a notion, because, well, if you're looking at effect size of a t-value, for example, you only have two things to compare: the mean of one group and the mean of the other group, and you're stating in your effect size measure if that is large or if it's small. We've also seen with performing, for example, the contrasts this week for the mixed designs ANOVAs, that you could get f values for the contrast of 4 points. So if you have an interaction we had an interaction with 9 points, 3 by 3, and one of the contrasts only focused on the top two of the one variable and the first two, for example, of the second variable. So you needed to compare 4 points, and you only got one indication of what that difference was in terms of an f value. So then you had to look at the data to see what's going on. And here, because you have a contingency table, yeah, you could look at it from this side to that side, or from that side to that side, and it's more about the question that you want to see answered, and stating what then the odds ratio, the effect size, is for that specific question that you're holding. So for in our example, it obviously, this the way that it's reported for this one is a logical one in terms of, I'm seeing that the relation between men and women that can whistle is about the same. So it's 0.5 as a ratio.
We don't see the slide.
Well, not really, but it comes close. It's not really different, but the relation between men and women that can't whistle, yeah, that's totally off to one direction. So it gives you the direction of what is going on, and that you can finally put in an odds ratio, which.
I'm sorry, we can't see the slides.
Oh, sorry. Good.
Thanks.
Good that you mentioned. So here you can see that the relation between males and females that can whistle is, well, close to each other. So in terms of effect sizes, I would argue that this ratio is not that low. So it's good to stand still, but again with what's how to interpret the ratio, right? So if it's 1, it's equal, and it could be a little bit higher than 1, and then it favors one over the other. in terms of the ratio, and that's what we're seeing here. It's not 1, so they're not equal, but it's a bit smaller. But this one, the relation that of between men and women that can't whistle, yeah, this one is totally off. It totally favors the amount of women. So we see in this odds ratio the essential difference that's showing up in our data. And by finally saying, well, give me then the odds ratio of whistlers to people that can't whistle, it favors, in terms of this ratio, the whistlers, in the sense that the skewness is not determined by the is determined by the bottom part. Otherwise, you won't have a high odds ratio. That's a lot of talk, right? Does that make sense a bit?
Yes, thank you.
Okay. We're done with the chi-square test. You're still alive?
Yes.
Very good. Again, I will stick around for some questions afterwards, and I'll see you tomorrow for Bayesian statistics. Bye, everyone.
Bye.
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 Bye.